So yeah, I will talk about Legendrian contact homology for Weinstein handle attachments in higher dimensions. And thank you for the invitation. Very glad to give this talk. So this is a bit work in progress, but hopefully I can find someone to discuss these things with after the by performing this talk. I will find some people who wants to discuss the things I haven't completely worked out yet. And the plan for today is to first say something about Weinstein handle attachments, for those of you who are not that familiar with that, and also give a short introduction to Legendrian contact homology. And then I will describe a particular geometric setup which I need to be able to describe the Legendrian contact homology for attaching spheres of Weinstein, of critical Weinstein handles. And then if time permits, I will show this in an example, a Weinstein handle decomposition of T star CP2, and with that compute the singular homology of the free loop space of CP2. So that's the plan. And I guess if you have any questions, you can raise your hand. I'm not completely sure how that works, but I guess I will be interrupted if there are many questions. Okay, so let's start with Weinstein handle attachments. So a Weinstein domain is what you get if you take the standard symplectic to n ball and attach something called Weinstein handles. So this ball, it has a Liouville vector field, so a vector field pointing outward the boundary, and these Weinstein handles also have a Liouville vector field which points inward here, where you can attach them, and points outward up here. So that means that you can extend the symplectic structure from the ball over the handle and still have a Liouville vector field pointing outwards. And this induces in particular a contact structure on the boundary. And then you can perform these handle attachments inductively. So first you attach this handle and then next handle and so on. And this K indicates that the Weinstein handle is of index K, and it's attached along an isotropic SK-1 in the contact boundary. And because of this Liouville vector field, we get that the highest possible index of a Weinstein handle equals n, so half the dimension of the manifold. And these top index handles are attached along Legendrian links, lambda attach in the subcritical part of X. So the subcritical part is when you attach all handles except for the top index ones. So another way of viewing X is to see it as the subcritical part together with the top index handles attached along a Legendrian link of Sn-1. So in this picture you have X sub here, the subcritical part, and then you attach index n handles here and here. And the reason why I want to view X like this is that then you can compute the symplectic homology from something called the Legendrian contact homology of these attaching spheres. So you get the symplectic homology of X is isomorphic to the Hochschild homology of the Legendrian contact homology complex, or the Chekhanov-Eliashberg complex of the Legendrians lambda attach. And the reason for this is that you have an exact triangle with the symplectic homology of X and the symplectic homology of X sub, and then this guy. But the symplectic homology of a subcritical Weinstein domain vanishes, and you get this isomorphism. So that's why it's interesting to compute the Legendrian contact homology of attaching Legendrian spheres in subcritical Weinstein domains. So that's the motivation of why I want to study this. And this has been studied in dimension 4 by Ekholm-Ng, and they describe a way to compute the Legendrian contact homology of the attaching lambda by using a Gompf diagram. So here you have lambda attached, and here you have the attaching spheres of the index and 1 handles. And in this region, you can use, if you know about Legendrian contact homology, you can use the techniques in R3 to compute Legendrian contact homology in here, and in the handle you get an sub algebra which is infinitely generated, but where the differential can be given completely combinatorial and can be described explicitly, so you can compute the Legendrian contact homology of this guy. And what I want to talk about today is a generalization of this to higher dimensions. And as I said before, this is work in progress. Okay, so let me say something about Legendrian contact homology. So we start with the easiest case, namely in one-yet spaces. So a one-yet space of a smooth manifold M can be seen as the cotangent bundle of M times R. And it's equipped with a one-form alpha, which is the z minus y dx. So x is the coordinate on M, y is the cotangent, the coordinate in the cotangent fiber, and z is the coordinate on R. And the kernel of this one form gives a distribution of hyperplane fields. And this gives a contact structure. And being a contact structure means that these planes, they move in a way so it's impossible to find submanifolds of dimension greater than M, which are tangent to this contact structure. So the dimension of M is the highest possible dimension of a submanifold to be tangent to this contact structure. And such a submanifold is called Legendrian. And the easiest case, I guess, is when M is R, then you get the contact planes like this, and it's invariant in z direction. And Legendrians then must be one-dimensional, so they are not, which are everywhere tangent to these planes. And if you have a Legendrian in one-yet space, then you can look at the projection to the cotangent bundle, and then you will get an immersed Lagrangian. So you have two very useful projections, the Lagrangian projection, which is the projection to cotangent bundle, and the front projection, which is the projection to M times R. And as I said, you get a Lagrangian from a Legendrian immersed, so it will have double points. And in the front, you get something looking like this. So instead of vertical things like this, you get the cusps. So if you don't know about Legendrians, just think about these two pictures in the talk. Have these two pictures in your mind. And now we want to associate an algebra to each Legendrian. And this algebra is generated by the double points here. And it is this algebra that we want to define a differential on, so that we can then talk about homology. So the double points here in the Lagrangian projection, well, they correspond to something called Reb chords of lambda. So these are solution curves of something called the Reb vector field, which is associated to alpha. And in the case of a one-yet space, the Reb vector field is just given by this z. So in this picture, we will have two Reb chords, one here and one here, because points in the front projection must have the same slope to be kind of identified when lifted to the one-jet space. So these double points, or equivalently Reb chords, they generate an algebra, which I denote A lambda and I indicating which space we are, and they generate this algebra freely, so no relations. And I will assume that we have coefficients in Z2, so in one-jet spaces you can work with other coefficients, but for now we just consider Z2. And this algebra is graded by a Conley-Sender index, which is a Maslow type index, which I won't talk about, but at least we get the grading. And now we want to define the differential. So the differential of a generator, this is a sum of a count of elements in certain moduli spaces multiplied by a word of generators. So B1 to Bm are generators of the algebra. And this modular space, A fat B, well, fat B is just a tuple of the letters in this word. So this is a moduli space of punctured rigid pseudo-holomorphic disks in T star M with boundary on the Lagrangian prediction of our lambda. So let me just explain this in an example. So here we have an example of a projected Legendrian, which has 6 double points, so 6 generators, A1 to A6. And we see that at each double point, we get 4 regions. And I have put plus signs here on 2 of the regions. And here we should have a plus here and a plus here. And everywhere else we should have minuses. And this disks in the moduli space, they are polygons with a positive corner at A and negative corners at B1 to Bm. And this B1, B2 to Bm come in a counterclockwise manner around the boundary of the disk. So for example, if you take the derivative of A1, which I do over here, then we have one disk here, the blue one, which has a positive corner at A1 and no other corners. So this gives 1 in the differential. And then we have another disk with positive corner at A1 and then negative corners at A5 and A4. So this gives the word A5, A4 in the differential. So this is the differential of A1. And then this can be generalized to one-jet spaces of NEM. And one can prove that the differential squares to 0 and decreases the grading by 1. So one can form the homology, and this homology gives a Legendrian invariant called Legendrian contact homology. So it's invariant under, if we have our lambda and then change it in a family of Legendrians, then this is the Legendrian contact homology is invariant. And in the case of one-jet spaces, this is rather well studied. So there are some tools to make this easier to compute. Well, when M is equal to R, we get this nice description just to find polygons. But for general M, in high dimensions, you have to solve a d-bar equation, and in general, that's very difficult. But there are some tools to make this easier to compute. For example, Morse flow trees by Ekholm, where you reduce this d-bar problem to a Morse theoretical problem, and cellular homology by Rutherford and Sullivan. So this works when the dimension of the Legendrian equals 2. But then you get a nice tool to compute the algebra. So Legendrian contact homology in one-hit spaces are kind of nice. But the problem for us is that we have to consider Legendrian contact homology in the boundary of a subcritical Weinstein domain. And this is defined in the following way. Well, again, we have an algebra generated by the Reb chords of lambda. But now the differential counts pseudo-homomorphic disks in R times the boundary of X. And the disk should have boundary on R times lambda and should be anchored in X. So that means that the disks now look like this. So up here we have a Reb chord A, which the disk is asymptotic to. And then we follow the boundary, which is on R times lambda. And here we come to a Reb chord B1 and B2 and so on, Bm, which then gives the word in the differential. But now we can have interior punctures, which are asymptotic to Reb orbits. So Reb orbits are periodic solutions to the Reb vector field. And these punctures should be kept off with CP1s in X. So at least it seems to me that these things are even worse to find. So my goal is to reduce this to something that can be computed using one-hit space techniques. So this is inspired by what Ekholm-Ng did in dimension 4. And I will try to explain for you how I'm trying to achieve this. Any questions so far? Oh. Okay.
Just so, sorry, I had a question. So when you say one jet space techniques, which one jet space are you just trying to, you're trying to reduce it back to a problem in X? Is that?
No, so we will have to consider some different one-hit spaces and then glue things together.
Okay, okay, now I understand better.
Yeah. So hopefully this will become a bit clearer. So to do this, I need a particular geometric setup, which I will now explain. So first I need some assumptions on the subcritical handles and in the subcritical handles. So first of all, I assume that I only have one subcritical handle. So this also works with several subcritical handles which are far away from each other. So maybe one sitting here and maybe one sitting here. But to simplify all formulas, we just assume we have one subcritical handle of index k. So it's given by the 2n minus 2k dimensional disk times the cotangent bundle of dk. So it has a core dk, which is the zero section of this cotangent bundle, and it's pictured in green here. And a co-core, which is then d2n minus 2k times the cotangent fiber over 0. And I also need some assumptions on lambda in the handle. So I will assume that lambda intersects the boundary of the co-core in a Legendrian lambda sub, which is a Legendrian in the boundary of d2n minus 2k. And it's over so it's 0 in this direction. So you have a Legendrian in S2n minus 2k minus 1 sitting over the co-core. And then to get the rest of lambda in the handle, I assume it to just be given by the Liouville flow of this one. So you get a cone on lambda sub. So it's something like shrinking into the handle, but looking like lambda sub over each point. So it's topologically, it's just lambda sub times the core. Yes, because this will simplify the Reb dynamics. And to explain this, let us put some coordinates.
Can I ask a quick question? So yeah. are these I don't like fully understand, but are the assumptions topologically restrictive, or can you attain them by performing some Legendrian isotopies?
I don't see why they should be topologically restrictable, but I'm not completely sure. But it doesn't seem to me that it should be any restrictions. Is that
thank you.
Yeah, so at least if you can find such things, you can do this. And then I should think more about if this really puts some restrictions on it. Okay, but assume we have this picture, and then put coordinates x, y on d2n minus 2k. So view this as the unit disk in C n minus k, and then complex coordinates x, y, and then coordinates q, p on the coordinate bundle. So q is coordinates on dk, and p are coordinates in the coordinate fiber. And this is just to remind you about what I assumed on lambda in the handle. So it's constantly 0 in the p coordinate. And the Reb flow will be hyperbolic in the t star dk direction. So it's just flowing away from the 0 section and from going out. So if we start at the point in the on lambda in the co-core, then the flow will be reduced to the one on S2n minus 2k minus 1, because, well, lambda is in the boundary of D2n minus 2k. And in D2n minus 2k, the Reb flow is just the one we have on standard S2n minus 2k minus 1. And if we start at some other point on lambda, then we will never return to p equals 0, because we're flowing away from the 0 section. So this means that the only Reb chords in the handle are located at the co-core, and here the Reb dynamics restricts to the one on S2n minus 2k minus 1. So the Reb chords in the handle are precisely the Reb chords of lambda sub. And since lambda is the cone on lambda sub, and I guess it's the maximum principle, which implies that there are no pseudo-holomorphic disks. So, or maybe I should say, so if you have a pseudo-holomorphic disk with a positive puncture at the Reb chord in the co-core, so here, then this disk must have all negative punctures at Reb chords in the co-core. They cannot escape the handle, because it's kind of going into the center. So this means that we get a sub DGA, which is just given by the DGA associated to lambda sub in S2n minus 2k minus 1 in the handle. And if k is less than n minus 1, then this is quasi-isomorphic to the DGA of lambda sub in the one-year space of R n minus k minus 1. So then we can use techniques from one-year space to compute it.
Excuse me.
Yeah.
What is the relation between the the Conley-Sender index of those chords as seen as chords in S 2n minus 2k minus 1 and seen as chord in the whole manifold.
Here you don't get any shift in the grading because you can view this thing happen at the co-core as a minimum. So it should not be any shift.
Okay, thank you.
So you have this relation, and even without grading shift. And if k equals n minus 1, then this dj of lambda sub in S2n minus 2k minus 1 is given by the handle dj given by Ekholm-Ng. So then you get infinitely many generators, but you get a differential which you can describe explicitly and given in their paper. Because then when k is n minus 1, then this I guess only you only get S1 here, so it's not that nice anymore, but you can still compute things. So this is what we get in the handle, but now the problem is outside the handle. So we need some assumptions also outside the subcritical handle. So I assume that we have a Darboux ball in the boundary of B2n, which contains the attaching region of the index k handle, which I picture with small balls here. And this Darboux ball should also contain lambda, the part of lambda outside the handle. So the red part is lambda. And now we have some generators outside here, and we can have pseudo holomorphic disks with these generators as positive punctures going into the handle, and maybe go around or go to punctures in to Reb cores in the handle. And this we want to prevent. So to do that, we need to have a closer look at the attaching region of the index k handle. So let n be this attaching region, and then this is contactomorphic to the cotangent bundle of the attaching sphere, so sk minus 1 times d2n minus 2k times an interval. So this d2n minus 2k is just the d is kind of identified with the d2n minus 2k in the handle. This is the cotangent bundle around the boundary of the core in the handle, and then you need this interval to go into the handle along the boundary. So because of our assumptions on lambda in the handle, get that lambda intersected with the attaching region is just the zero section of the cotangent bundle times lambda sub times the interval. So here we have the analysis sk minus 1 times the interval, and over each point you have lambda sub sitting. And because of the conical behavior of lambda in the handle, you also have that it lambda sub like dives radially conically into the handle. I tried to picture it here. So the radius is decreasing when you go closer to the handle. Like this. So then you can have a lot of disks coming from this Darboux ball outside the handle, entering the handle, having boundary on lambda. To prevent this to happen, I will introduce something called dippings. So this is just to remind us what lambda looks like in the attaching region. It's from the previous slide. And now we want to modify this function, which is decreasing the radius of lambda sub, to have we want to replace it with some other function FOQ, which has a minima and a maxima, min and max, because outside here is the Darboux ball. This is outside the handle. So then if we have a disk who wants to enter the handle, it will stop here. So over this min, we will have our lambda sub, and for each reb chord of lambda sub, we will have a reb chord of lambda because of this min, and the same thing over the max. If we replace q squared up here with FOQ, so we Legendrian isotope lambda in the attaching region to be given by to have radius shifting with f instead of q square. But then we will have an sk minus 1 word of reb chords here at the minima, and the same at the maxima. So we get a more spot situation, at least if k is greater than 1. So what we do is that we introduce max and min also on sk minus 1. So we change f to a function f tilde defined on both sk minus 1 times I, which still has a min and a max in I direction like this, but also a min and a max on sk minus 1 like this. So lambda in the attaching region is now given by x in sk minus 1 times f tilde of xq times y, where y is in lambda sub and q is in this interval. So then we get 4 critical points for f tilde, which I denote by m, s, n, and t. So this is in the attaching region, and n and s also shows up on the boundary of the core in the handle. And from before we have this h, which we can view as a minima. And now, since we have critical points here, we will, for each generator of the dj of lambda sub in S2n minus 2k minus 1, get 5 copies of generators of the algebra of lambda. So we get 5 reb chords of lambda for each reb chord of lambda sub. These reb chords are sitting over m, s, n, t, and h, and I label them by at, an, and so on to indicate where they sit. So we created a lot more generators by doing this, but we will get some kind of control of how they interact with each other. Or yeah, so how they interact means what are the rigid pseudo-homomorphic disks with these as punctures or as asymptotic reb chords. And to understand this, I want to use abstract perturbations. And first of all, assume that k is strictly between 1 and n minus 1. Because in the k equals 1 case, we don't have this spot situations, then things simplifies a little bit. And if k is equal to n minus 1, then we have this huge algebra, at least in the handle, not necessarily outside here, but we get, get something different. So I don't want to talk about it here. So we focus on this case. And here I tried to picture the flow of f tilde. So recall that f tilde was this function defined on sk minus 1 times I with these critical points. And m was a min, so all flow lines is going to this. S is a max in I direction, but a mean in sk-1. So the flow lines look like this. And n is a max both in I direction and sk-1. So it has flow lines going everywhere in the touching region and also into the handle here. And t is a max in sk-1, so it has flow lines along sk-1, but it's a mean in I direction. So we have a flow line going from n to t. And now I want to use the pseudo-holomorphic disks of lambda sub together with these flow lines to find the pseudo-holomorphic disks of the copies of the generator sitting here. So, for example, if you have an A sitting at S, so an AS, and a pseudo-holomorphic disk in S2n minus 2k minus 1 with the positive puncture, this A, then with this disk sitting at S, just flow it down a little bit, and then you can use an abstract perturbation to flow one of the negative punctures up to S again, and the other ones will flow down to M, and this should give a rigid disk for AS, and similar at the other ones. So this is using ideas from the paper by Ekholm and Kalman, and I guess there are other papers also treating with similar things that I should read. So here we enter the work in progress part. So what we should give, or what we should get here in the dipping region, in the handle, is that if we have a word B1 to Bj in dA, in A lambda sub S2n minus 2k minus 1, then we should get a similar word for DAL, where L is Tn, Sm, and H. And similar means the following. So at M and H, we have sub-algebras. So then we just get a similar word, but now with copies sitting over M and over H, respectively. And then over S, as I tried to explain, and for each letter in this word, we get one of the letters staying at S and the other ones flowing down to M, and similar into the handle. So we have one letter staying at S and all other ones flowing down to H. And this we can do for all. We can let any of B1 to Bj stay at S, so we get the sum from I equals 1 to j of such words. And similar for T, then we have a flow to M. So we should get sums of words like this. One guy staying at T and the other one's going to M. And for N, it's a little bit more complicated because then we have flows everywhere. So then we get a mix of letters, and I would say that the conjecture is that, so this L1 to Lj can belong to Ts, M, or H, but the conjecture is that it's for each word it's constant in these letters. So either you get B1t to Bi minus 1t, B1n, Bi plus 1t, and so on to Bjt. Then you get this for all of these copies, but I still need to prove this, and hopefully some of you want to discuss this with me. But at least we should get words of this type. And in addition, we also get that the differential of AS contains AM plus AH, because here we have an index 1 flow line, or the index shift between S and M is 1. So we have one rigid flow line. So we can just flow S down to AS down to AM, and the same thing in the handle here. And similarly, we get that DAN contains AT. And these formulas then gives the differential in the handle and the dipping region. So
can I ask about this slide? So
yeah,
you said, you're trying to prove this. So what does it mean? It means that you expect that there are holomorphic curves which realize these expressions for the differential,
yeah.
and that somehow maybe it's not obvious how to count because of lack of transversality. Okay? Okay.
Yeah.
Thank you.
So yes,
Another
exactly.
question also about because I don't know about this the Ekholm-Ng stuff that you mentioned, but and I guess I should know this flow tree stuff better, but how does this kind of deviate from a typical situation in which the flow trees are rigid? Like, where does the lack of transversality come in?
So I guess the problem is the thing, yeah, that you have this more spot situation from the beginning, and then so yeah. To be honest, I don't really understand this completely yet. And I think understanding it would help to compute this thing. But the lack of transversality come from this more spot situation.
So yeah, so it comes from the like transitioning from more spot to Morse.
Yeah. At least this is how I understand it. So if someone knows better, can.
I think that's correct.
Okay, yeah, great. Okay, so at least something like this should give the differential in the handle and the dipping region. So like, in some sense, no matter what this expression is, we see that we can compute the differential in the handle from this lambda sub in S2n minus 2k minus 1, which we can see as something in a one-year space, and these flows in some sense. So we don't have to look at these anchored disks. And also the reason for us to introduce the dippings was to prevent the disks outside the handle to enter the handle. So now we have disks outside the handle will stay outside the handle. And again, this means that we don't have to care about anchor disks outside the handle, because then it's just in the boundary of B to n minus 2k. So I think it's written in Ekholm-Ng's paper about why we don't have to consider anchor disk in that case. So the result, or the conjecture, maybe because everything isn't completely proven yet, and again assume that k is strictly between 1 and n minus 1, just to simplify things for this talk. Then the DGA A of lambda in X is quasi-isomorphic to an algebra generated by the Reb course of lambda in the Darboux ball outside the handle, together with generators AT, AN, AS, AM, AH for each Reb chord A of lambda sub. And the differential is given by a count of rigid pseudo-holomorphic disks of lambda intersected the Darboux ball in the Darboux ball. So then we can just do the count as if we were in R2n minus 1. But we have to include lambda in half of the attaching regions in the gray part here, because we introduced this min here, or the dipping. So the disks from the Darboux ball, some of them will come in here, these points. So this part of lambda needs to be included in the Darboux ball. And the differential is given by the formula from the previous slide in the handle and the dipping region. So, and again, this should mean that that we don't need to consider anchor disk. We can just split up everything in to compute the DGAs for lambdas in one-jet spaces, and then putting the differentials together to get the differential of lambda in X. So any questions about this? Otherwise, I will show you an example of how this can be done without caring about dippings. Okay, so we move on to the example. And the motivation for this example is to compute the singular homology of the free loop space of CP2. We'll use two theorems. The first is by Abondadolo, Schwarz, Witter, Bo, and Salomon Weber. I hope I didn't forget anyone. Which says that the singular homology of the free loop space of M is isomorphic to the symplectic homology of the coordinate bundle of M. And then we have a theorem which I mentioned before by Bourgeois, Ekholm, and Liashberg that says that the symplectic homology of, in this case, the coordinate bundle of M is isomorphic to the Hochschild homology of the Legendrian contact homology complex of the attaching sphere of the top index handles in a Weinstein decomposition of T star M. And now I want to use this to compute the singular homology of the free loop space of CP2. So we'll compute this guy, the Legendrian contact homology complex, and then we just use this to get the homology of the free loop space. And first we have to find a Weinstein handle decomposition of T star CP2. And well, such a handle decomposition can be given by a handle decomposition of CP2 thickened up. So, so we take the standard handle decomposition of CP2, namely we attach a two handle along a circle epsilon in the boundary of B4. So epsilon is a circle of framing 1. And then we attach a four handle along the boundary of the resulting manifold. And then we thicken things up to get T star CP2. And another way of viewing this is to consider epsilon as a subset of the Legendrian lambda tilde, which is the real part of the boundary of B8. This is sitting in C4. So this is a Legendrian S3 in S7. And then we let lambda in the boundary of B8 with the two handle attached along epsilon be the Legendrian submanifold given by replacing a neighborhood of epsilon in lambda tilde with the standard Legendrian cylinder in the boundary of the two handle. So this standard Legendrian cylinder is what you get if you, so here over the co-core you have D4 times D2 if this has index 2 in dimension 8. So this D2n minus 2k is now D4. So the boundary of it is S3. And in S3 we have the standard Legendrian S1. So we take this as our lambda sub and then just apply the Liouville flow to get the standard Legendrian cylinder. So we create lambda by gluing this to lambda tilde. And I try to picture this. So here we have lambda tilde is just standard Legendrian S3, like this. So it has, in the front projection, it has a cusp, which is homomorphic to S2. And here along the cusp, we choose to put our epsilon. So in this green circle, I zoom in to find this one. And here we have epsilon, which is Legendrian unknot, which intersects the cusp in 2 points, like this. And here we attach our two handle. So the two handle will have core D2 bounded by epsilon, and the standard Legendrian cylinder, this two handle will look like this. We have the standard unknot going into the handle radially along at every point on the boundary. And we form lambda by removing boundary here and gluing in this lambda sub. Okay, so now we have to understand the DGA of the resulting Legendrian. And outside the handle, well, we notice that lambda tilde has one reb chord A of grading 3 sitting here. And this is away from the attaching region, so this will still be a reb chord of lambda. And from A, we have an S2 family of Morse flow trees going to the cusp edge. And if you're not used to Morse flow trees, so think of this as a boundary of pseudo-holomorphic disks. Get an S2 family of them intersecting the cusp in 1 point. And we will also have this in the attaching region. And these flow trees will intersect epsilon either 0, 1, or 2 times. So the red ones intersect 0 times, the purple and the yellow one intersect 1 time, and the green intersects 2 times, 1 here and 1 here. And the reason for the purple and the yellow one not belonging to the same flow line is that this is in the front projection, so we have one more dimension for epsilon, so it will be skew everywhere except over these 2 points. And we see that the flow lines which do not intersect epsilon, they come in a 2-dimensional family. The ones intersecting in one point come in a 1-dimensional families, and we have a 0-dimensional family of things intersecting twice, and there's exactly one such tree. So this is how it looks like outside the handle. And inside the handle, well, lambda sub was just a standard unknot, so it has one reb chord, B of grading 1. So I picture it everywhere here, but the one we are interested in is sitting at the center of the core. So now we don't need to do this dipping procedure. We can trace our disks or flow trees without dippings because this is an easy case. So we're only interested in the copy of B sitting here because that gives us a reb chord of lambda. And we have this green flow line going to epsilon. So we have it also in this picture. And this gives us one rigid flow tree of lambda, because here in the cone over lambda sub over these 2 points, we have a flow tree or a pair of flow lines going from B out here on the boundary of the core, going into the center of the core over both these points. And this we can glue to the green one to get a rigid flow tree of lambda. So in this picture, we have the green pair of flow lines coming in, then they split up into the blue pair and the red pair, and both end at B in the center. So we get a flow tree like this, starting at A, and then it splits up to one blue one going to B and one red one going to B. And this means that the differential of A will be B square, and the differential of B will be 0, because here we have two flow trees, one going to the cusp here, and one going in the other direction to the cusp. And since everything is modular 2, this gives 0. So this is the DGA of lambda. It has two generators, one generator A of grading 3, one generator B of grading 1, and the differential is given as follows. And then if we take the Hochschild homology of this DGA, we get a singular homology of the free loop space of CP2. Yes, so that was everything I planned to say.
Okay, let's thank Cecilia. Are there any questions? And maybe while people are, yes, go ahead. No. Okay, I have a question. There is in this free loop space of CP2, there is supposed to be a tricky sign because of the condition of being spin or not being spin. Have you thought about this?
No.
Okay. I think, well, I actually think this was first, so this was first observed by Thomas Krog, which is that the homology, in fact, this statement of Viterbo cannot quite be correct. And the homology of the symplectic homology is not actually isomorphic to the homology of the free loop space, but rather by its twist by a local system. And the local system essentially comes from, the local system is trivial whenever there is a spin structure on the base of the cotangent bundle. And in this case, I believe that CP2 is not, I think CP2 is not spin. I haven't done the computation in a while. And so the signs are such that, you know, the such things are not gonna, should not quite work out. Now, the only thing I want to say is that this actually doesn't affect the strategy, because what is actually true is that you can do Floer homology with certain local systems, and you can do homology of free loop space with local systems, and then you can just go back and, you know, twist each side so that the signs are correct. So you should see somehow the correct moduli spaces, everything should be correct. It's just that at some point you have to decide whether something is a +1 or a -1, and that will affect the answer. Anyway, that ended up being more of a comment than a question. So does anybody else have any questions?
Yeah, I wanted to ask why, I was a bit lost in the middle. So, but why you can do the computation in the for the loop space of CP2 without introducing the deep-in region?
Because now I could understand the disks going into the handle, because this green thing goes into, is a disk going into the handle, but it should be the only rigid configuration.
And what is special there that makes you understand that disk?
I have an explicit example, and then everything is easier when you get something explicit to work.
Okay, thank you.
So like, I think like the bad thing you want to try to avoid is like a disk could go into the handle and then pass out the other side, right? And then you can't use, you want to completely use the one jet space Morse flow trees picture on the complement of the handle before it goes inside. So I think it kind of blocks that from happening, right?
Yeah, and if it goes around into the handle and out again, I need to have homology coefficients as well. Because now I just, I made some simplifications about coefficients also.
So can I, are there any more questions? Anybody else want to ask anything? I wanted to go back to this place where you said that, you know, you're trying to do this, maybe this was better for the discussion session. So maybe if nobody has any questions, okay, we should thank Cecilia again.